Okay, we're recording. This is the beginning of the second part of today's revision. So I'm going to be moving on to NMR. So in the chirality and NMR topic, I've just finished doing chirality. So we're going to be moving to NMR. So essentially, what we've got here is I've got the 60 minutes, 81%. That's all for chirality. So what I'm going to do is when I finish my NMR, I will add the total on here. I will add the uh, average out the percentage, and this is KQ is a knowledge quotient I've given it, so it's just how good my knowledge overall of the topic is. So for example, this energetics 2 actually should probably be not this number because this only covered the majority of the topic and not all of it. So we can reestablish that over here where we have another one on Monday, so it's fine. But yeah, so I'm doing that. So it should have my highest because we've already done 60 minutes. There should be my highest time, and then we can move to transition metals later, and then hopefully some biology. Haven't updated this since the 8th, which is obviously all of this is going to be. Not do this quickly. I'm just gonna pause and so I can do this. Okay, so that's now up to date. So nothing since the change at all. And then psychology, even though it's my most imminent exam, I'm just not gonna focus on that until a little bit later because slightly less, slightly less difficult in my opinion, um, to get top marks. These two are going to be definitely the hardest. So that warrants getting onto as quick as possible. So I'll just get up the NMR notes. Okay, so here are the notes for NMR, so you can read through this. Not as long as the chirality notes, or actually no, longer than the chirality notes. Somehow, really, these are only 2 pages. Wow. Okay, so NMR spectroscopy involves interaction of materials with the low energy radio wave region of the electromagnetic spectrum. Radio waves used in the proton NMR cause a hydrogen nucleus to change its spin state. Interesting. NMR spectroscopy is the same technology used in magnetic resonance imaging (MRI) to obtain diagnostic information about internal structures in body scanners, ED scanning for brain disorders. Brilliant. Equivalent hydrogen atoms. In hydrogen NMR spectrum, there is one signal for each set of equivalent hydrogen atoms. Ethanol has 3 groups of different hydrogen atoms. So yeah, we can see there that all of the A hydrogens are the same, all the B hydrogens are the same, and obviously there's only one C hydrogen, so it must be unique. So the reason they're the same is that they're attached to the same carbon and they have the same path through the molecule, if I would be interpreting that correctly. So if you go either direction from that carbon, it's the same for both hydrogens. That's essentially, I think, it. That would make sense for the one on the right here, which has these two HA groups, even though they're on different carbons, they take the same path through the molecule. So all 6 carbons are essentially the same uh, environment, same conditions. Yeah, that makes a lot of sense. It, so in addition, the intensity integration value of each signal is proportional to the number of equivalent H atoms it represents. So that's why the 3A group is the tallest, and then Three sets equivalent hydrogens, ratio 3 to 9. Yeah, we can just see all the examples here of how the groups work. So this molecule here, third one down. If I just use my mouse, this one here, we can see that it's a symmetrical molecule. What am I looking at? Oh, sorry, this one here, symmetrical molecule. So these two have the exact same conditions. These are different because there is a second, instead of an oxygen being here, it's a CH2 group, so it's not symmetrical. So they're all three are different. Yeah, and then carries on through these, and we can get the idea there. Okay, samples are dissolved in solvents without any hydrogen atoms, e.g. CCl4, CdCl3. This means that NMR solvent will not give any peaks. That is interesting. I haven't thought about that, and probably since I learned it, so that's a good thing to pick up on. CCl4 is a non-polar compound that's a good solvent for non-polar organic molecules. CdCl3 is a polar covalent molecule that's a good solvent for polar organic molecules. Okay. Calibration and shift. A small amount of TMS, tetramethylsilane, is added to the sample to calibrate the spectrum. Have definitely heard of this one. So these, as far as I remember, all of these will give the same, because it's completely symmetrical both ways. They'll all give the same shift. So they'll only form one peak, and it'll be extremely tall peak of 12, because there's 12 hydrogens all in the same environment. So, and then there's all these explanations here. So the spectra are recorded on a scale known as a chemical shift, parts per million, which is how much the field has shifted away from the field for TMS. TMS is used because it's a signal away from all the others. I don't know why. It only gives one signal. It gives a strong signal, so only a small amount needed. That's, I think, the 12 thing, because there's 12 hydrogens in the same environment, so that's why it's strong. It's non-toxic, it's inert, so it won't react with anything, has a low boiling point, and can be removed from a sample easily. So that makes sense. So all these things are required, non-toxic, inert, low boiling point, so it can be added to a lot of stuff. So the parts per million is okay. The blah blah blah, whatever that symbol is a measure in parts per million. The chemical shift, that's what it's called. Chemical shift is a measure in parts per million. Is the relative scale of how far the frequency of the proton signal has shifted away from that for TMS. Okay. The chemical shift depends on what other atoms / groups are near the hydrogen. More electronegative groups gives the greatest shift. Interesting. So the CH3 is not. I see. So so if we look at this example, I'm just going to zoom in on this a bit here. This is interesting. This is interesting for me to look at. So this CH3 is over here at 1. This CH3 group, which is, they're both CH3 groups, is all the way here over nearly at 4. So what I'm seeing from this is that the CH3 here is attached to a CH2 and then to a carbon. So none of these here are very electronegative. So the CH2 and the carbon it's bonded to. So the most electronegative thing that is anywhere near is the double bond oxygen here. So that's why it's so far over on the right near 1. And then this CH3 here, the carbon is directly bonded. The carbon which the hydrogens are attached to is directly bonded to an oxygen, which is much more electronegative, and that explains why the shift is so much. And then and here we can see the CH2 is kind of in the middle because it's not directly bonded to an oxygen like this one, but it is directly bonded to a carbon which is bonded to an oxygen, so it's kind of in between. That makes a lot of sense. At about 2.5, 2.3 there. So very interesting. And then we have some typical values. Um, so what I'm trying to see here is, so this is the chemical shift of a hydrogen attached to a carbon attached to another carbon. Is that what this is saying? Because okay, it's saying 0.7 to 1.2, which this is in the range of this one on the far left here. So, but this one obviously is nowhere near that, which is interesting. But I mean, we know the explanation for why. I interpret it as I interpret it. This makes sense. This graph makes a lot of sense with this. That depends on more negative gives the greatest shift. I mean, that makes a lot of sense. I'll just stick with that. This I'll take with a grain of salt, I suppose. I mean, I think I understand it. I think I understand it. Okay. So this hydrogen is very high, all the way up at 12. That's because it's directly bonded to an oxygen. So that makes a lot of sense, complete sense, because instead of being bonded to a carbon and an oxygen, which is this one here, which is the leftmost one here, it's directly bonded to the oxygen itself, and then that oxygen is bonded to a carbon, which is bonded to another oxygen. So we can see something similar here. It's 10 to 12 is the range expected. That's exactly where it is, so it makes a lot of sense. On the carboxylic acid. And then these two are making a lot of sense as well. So this one's going to be further, more shift, because it's bonded to the carbon, which is bonded to both oxygens. This one's going to be left shift because it's bonded to the carbon one further away. So, and then we have spin coupling in hydrogen NMR. So does this not cover carbon NMR? Because where are we talking about carbon NMR? Because this is all hydrogen NMR. Like, where's the carbon NMR? Is there a separate thing for that? Sorry, one moment. Doesn't seem to be. Maybe that's included in a different topic. I don't know. It's not included here, so I don't know. I'll just run with this. Spin coupling in hydrogen NMR. In high resolution hydrogen NMR, each signal on the spectrum can be split into further lines due to inequivalent hydrogens on neighboring carbon atoms. Yes, remember this very well. The splitting of peak is a number of inequivalent H pluses on or hydrogens on neighboring carbon atoms plus one. So for example, this one I'm seeing here, it would mean the neighboring carbon atoms have a total of 4 hydrogens on them. So we can see here, B, the neighboring carbon atom, which is this, has 3, so there's 4. And then this one here, the neighboring carbon atom has 2, so there's 3. And then this one, the neighboring carbon atom has 0, so there's 1. So that makes sense. So we can read the rest of this. So nuclei in identical chemical environments do not show coupling amongst themselves. The peak due to a group A will be a triplet. That's a B. Yep. Peak due to group B will be a quartet. What's next to a carbon with 3 H's? Yep. And the peak due to group C will be a singlet, as it's next to a carbon with no H's. Well, it's not next to a carbon at all, it's next to an oxygen. Okay, whatever. For 6 split peaks, it must use the term hextet or multiplet. Yep, makes sense. And then this is just pretty simple. This is just everything we've already done in a bit of a summary. So I believe, okay, these are the questions we've just done. So moving on here, and then we're moving on to NMR spectroscopy section 2, and we start off the lovely 4 marker. Don't you gotta love a 4 marker? Okay, 15 minutes in. Have about 45 minutes to spare. Let's try and get this done. We have, I think, 4 pages of questions. Yes. So these, the first 3, probably going to take the longest because we got a 7 marker here. So, but hopefully not the worst. Okay. See, 13 carbon in it. So where's the carbon NMR mentioned in this document? I don't know. I don't know. We could get up the physics and maths tutor. Carbon NMR notes. Because they do love their notes on physics and maths tutor. This is TMS, so this is hydrogen NMR. Once again, doesn't each other silane. This is a carbon NMR, carbon 13 NMR. So let's go over this because we clearly didn't have this. So this form NMR spectroscopy analyzes the different carbon environments in a molecule. Different environments are shown as peaks of different chemical shift values. Is that again? Is that chemical shift? Like, why is this symbol not this symbol? Why are they different? I don't know. Okay. Carbon environments that are near to an oxygen have chemical shift values that are shifted to the left. It's because the oxygen is very electronegative and changes the bond environment and how it absorbs energy. Molecules that have symmetry may display fewer chemical shift peaks than the number of carbon atoms in the molecule. Therefore, in these cases, it's important to look at a given molecular formula of compound or decipher its displayed structure. Line of symmetry. So is this? So I'm presuming these two are is this one. These two is this one, and these two are this one. Makes a lot of sense. 3 environments, 3 peaks, and then it says here molecule 1, 2, 3, 6 hours, but then it has 3 peaks. Do the symmetry of the molecule. Okay, pretty simple. And then HNMR, which is already covered, which seems to be what everything is going over. So thank you, physics and maths tutor. You've covered everything we need to know. So let's start with the question. So questions about carbonyl compounds of molecule C5H10O. So that would be some kind of pentanol. Probably, maybe. That's a terrible assumption to make. I don't know. Probably not, actually. Let's just go with the question. An aldehyde with a molecular formula C5H10O has a 13 carbon NMR spectrum with 3 peaks. The high resolution hydrogen NMR spectrum has 2 peaks and neither of them is split. Deduce the displayed formula of this aldehyde. So it'd be very useful to be able to draw on this. because I would like to do that. However, I doubt it's going to be possible. It will be soon. I will have that set up soon. I guess for today I'll just have to do it um, on my own paper, and then I'll just show the answers because I don't have another way of doing it for now, but it will change soon. It will change soon. Okay, so first thing, 3 peaks. So 3 carbon environments. That's pretty. So that's pretty useful. So I'm gonna draw out. I'll start by drawing out a bunch of uh, pentanoic structures, pentane structures that have only 3 peaks, which means it's going to be relatively symmetrical, is what I'm thinking. So if we have, for example, an OH group here in the middle, so if you can imagine, oh, this is really difficult for me to explain without some way to draw. I wonder if I can duplicate this somehow. File, make a copy. Maybe this will allow me to draw. Ugh. Okay. Ugh. Oh, and I can change the folder here, so just select my drive and make a copy. That makes it easier. Okay, so now I should be able to draw on it, right? And I'll draw. So once displayed formula, I'm gonna do the. Can I draw? Is it like a drawing? Give me a moment. Okay, so my solution to this here is MS Paint. So what I've drawn right now is this. O and H. So that's what I've drawn. So now I'm thinking, if we go back to the question quickly, one second. We have uh, 3 peaks. So what we've drawn will have 3 peaks. If we go back, this will have 3 peaks. We look there. If I just go back to it, you'll have 1 peak here. Oh, I've just labeled them. In fact, put this in here. I can. That makes this easier. Sorry, I need to change it. So, here's a question. It's just, I don't know how to fit this in. There we go. So, oh, that's a bit off screen. Okay, wait, let me just move over so we can do a new drawing here. Okay, so as far as what makes sense, high resolution hydrogen has 2 peaks and neither of them are split. Interesting. So I'm thinking if we have, oh, that is not what I'm looking for. That is also not what I'm looking for. I don't know what I just recorded, but I have this up, so I'm gonna try and use this. So let me just delete that. Okay, I'm returned. I'm going to be eating my dinner while recording this, so it might be a bit mouthfully, but okay, so have to take this slow. Um, 5 carbons and only 2 hydrogen NMR peaks. That is very interesting to me. How is that possible? So that makes me think this is not an alcohol. Maybe makes me think it's some kind of ketone. What I think is very possible here is we have this. So what we have here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. This is one group, and this is the second group. We now have 3 carbon environments. These 3. 1, 2, 3. And we have 2 hydrogen environments. 1, 2. I think this is the answer. That's what I'm going to go with. I'm going to keep this here. I'm looking up. Sorry. I'm going to write this down on my paper. So C, 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 O, C, C, and obviously in the exam, I'm drawing every single hydrogen here because it is, of course, displayed formula. Okay, we can move on from that. Here, so that's question 1. Oh, but we're not done. Justify your answer by referring to both NMR spectra. Does that want an explanation? Potentially it does. So I'm gonna assume here that I can use this what I drew with each hydrogen and carbon um, group uh, environment, sorry, labeled. I'm assuming that is a suitable explanation for, you know, the conclusion I came to. Yeah, so I think we should move on. Okay, so it took me a little while to eat, so I might not have time to finish this whole section, but I should be able to get maybe this question done, or at least kind of a start on it. So, um, data from the high resolution hydrogen NMR spectrum of the ester Q are shown in the table. So we know it's an ester, so already a big help. Part of the structure of Q is shown. Complete the structure of Q. Justify your answer by linking protein environments in your structure to the relative peak areas and the splitting pattern of the peaks. Okay, so we have the chemical shift, the splitting pattern, and the relative peak area, and we know it's an ester. So if I remember, esters are formed from carboxylic acids and alcohols. So we have this here, which looks like part of a carboxylic acid. So imagine there was an H there, but obviously this is the H that's removed in the when the water is removed in the esterification reaction. So kind of assuming the rest of it is going to resemble an alcohol but without the OH. So just a So just like an alkane. Um, okay, we don't have like a molecular formula or an empirical formula. Um, but we know we have 4 hydrogen environments, and we know 2 of them are distinct and isolated, like not bonded to a carbon with anything on it. Or not bonded to a carbon which is bonded to a carbon with anything on it. Alternatively, they could be bonded to a oxygen. So first thing I'm gonna do is I'm gonna draw this out. So if I screenshot the question, and I will kind of just repeat the what I did with the last one. So I'm just gonna quickly open up a new tab and put this up. This up here. Perfect. And that's gonna work. Perfect. Put that in the top corner here. Oh, that's a bit out of. There we go. Okay, so we have. Okay, what's going on here? We have. How do I? A carbon here. So I can kind of like cross that one out. I might do that, just like cross this one, because we know this is this here. Can't draw a circle, but. So we now just have to figure out what the rest of these are. We have no other hydrogens in this, so we have a 3, a 4, and a 6. Okay, so there's going to be some symmetrical nature to the rest of this. So what if we're thinking relative peak area of 3? Maybe there is a CH3 on the end somewhere. But it's a singlet, so could make some. Okay, so I am feeling that we're going to. Okay, how do I distinguish these? Chemical shift is pretty low in this one, which kind of makes me think this might be R that we have here, because it is bonded to a carbon which is bonded directly, but this one could be bonded to a carbon which is bonded to an oxygen. So probably should keep that in mind. They're both singlets, which is interesting. So how could a quartet work? 4 and it's bonded to. So quartet is obviously 2 CH2s. Like that's pretty much what I would assume. But the relative peak area is also 4. That is also very interesting. Okay, no, oh, okay, I see. So the quartet is going to be bonded to one of these. So presumably this one. So I don't know why it was paused. I'm not sure why that happened. I'm wondering maybe whether I'm running out of storage. Because I was explaining for a bit there and it did say paused. So hoping that it will not pause itself again. Um, but yeah, I was just kind of saying that maybe something. I'm misremembering something about esterification itself, which is, I think, pretty possible. So yeah, I've kind of made the assumption that this top one here is this group on the bottom left here that we see in the question. However, and I know we have probably at least 3 more carbons, so I'm just kind of seeing whether any of this works. So we have at least one more group that's not bonded see, this is interesting. Okay, I figured out why it's pausing. Every time I press Control Z um, to remove something, it pauses. So when I'm just gonna, if I do something like that, I'm just gonna press the back button and it won't pause. So hopefully that fixes the problem. Okay, so what I'm thinking possibly here. I mean, what if it's like a dial? A dial. What is a dial? No, that doesn't. And also, version of the S to Q are shown in the table. No, an S to what? This is legitimately very hard to get. I think not 100% sure what I'm trying to go for. Um, yeah. Um, hmm. Maybe one of these carbons has a. Wow, this is very challenging. I'm wondering, is it possible that it's something like, okay, this is a bit of a long shot here, but um, because I haven't figured out fully whether this works, but this would have a relative peak area of 6 if this was an environment. Now it's attached to a triplet, which means this would have to have 2 hydrogens on it, which is not possible. But I'm wondering how something with a relative peak area of 6 can be bonded to something with 2 hydrogens on. It's very interesting. Um, how is that possible, actually? How is it possible? Because I'm assuming something with a relative peak area of 6 is just 2 CH3s. Unless I'm missing something really obvious, and this makes sense with the chemical shift because it's very far from oxygens. Um, but it doesn't make sense with the. How can you possibly have that? Like for example, if this was or like this was a double bond, and then this had a hydrogen, and this had 2 hydrogens or something. I don't know what's going on here. This is just a really random structure I've just made. Quartet. None of this makes sense. Relative peak area 4. No, no, no. None of. Yeah, I've paused again. Apologies. But I was just saying this has actually stumped me quite a lot. There's. I don't think it should be that hard. Um, but it is very difficult for sure. Like it's very gettable, I think. Just for your answer by linking the proton environments in your structure to the relative peak areas and the splitting patterns. Hmm. Like we're gonna have paused again, unfortunately. But yeah, we have. I was saying we should have some very low chemical shifts, so they're gonna be quite far away from our oxygens. The highest one is. Ooh, okay, okay. I have a somewhat interesting idea. So what if that doesn't work? Wait, that doesn't make any sense, does it? That looks really wrong. This is not this is not something that's possible. Two consecutive double bonds? That's not possible, is it? No, this is going out of feasibility here. So what? There's a carbon attached to this oxygen. That's pretty clear. So what is this one? So there's a triplet here. This is a relative peak area of 6. Because I was going to say if this, for example, was 2, that would make sense for the triplet, but then it would not make any sense for the chemical shift. So the next one that makes sense would be this, 1.43. So actually, okay, I'm going back to my previous, okay, actually I'm going to remove this. Assumption that this was this one. I think this here must be the top one, and this must be this one. So I'm going there. And then I think this one has to have relative peak area of 3, which means 3 hydrogens attached, which is impossible. What? This is very difficult for me to understand. What I think I'm going to do here is leave this one, go back to our questions, and then actually just check out the answer for this one, because very much struggling. So let's just quickly mark this first one that we got. That does not look like what we got, does it? Why does it have to be an aldehyde? Whoa, we got this wrong. That's the question. C5H10O, 3 peaks. I definitely have 3 peaks in mine. And 2 peaks. This definitely has 2 peaks. So why is this one the only one that's correct? Oh, because it says it's an aldehyde. Oh, wow. Okay. Did not pay attention enough to that. So, okay, so the only thing that's possible is then this, what they've shown here. Yep. Also makes plenty of sense. Did not see that. So I guess these are probably the only 2 possible solutions. I think I must basically get 0 marks because I've got the structure wrong there, unfortunately. And then this one is just completely stumped me. So let's look at the answer. Wow, so wait. This oh, that makes so much sense. So there was no hydrogen environment on this carbon. So that explains why I was struggling to place this carbon bonded to the oxygen, because I was kind of just assuming it was only bonded to one other carbon. But that is very hard to visualize, I'd say. And then yeah, these 2 are the same, so that's why it's 4, and then these 2 are the same, that's why it's 6, and then we have the 3 here. Wow. And then all of the shifts make sense, and this was the 2.5, the top. Oh, I don't know where it was now. Oh yeah, this was the top one. So had it for a while, kind of couldn't place it properly, but makes a whole lot of sense. But wow, that is a rough question. Okay, I think um, I should finish there. Um, I do have to go now, so I think it's a good opportunity to leave it there.
Um, I will add the extra 45 minutes we have spent on this to the document. If I just come up here. So this should end up on 105 minutes, which is a lot. But since we got 0%, well, I'm not going to average it of 0% because I answered one question, I got 0 out of 4. I suppose that just means we divide. I mean, should I really sacrifice all of that greatness for a much worse? Because I'd just be dividing 81 by 2, which is 40.5, which is just 41, which is a very bad percentage. I don't know if that's deserved, 41%. So I might just leave it at 81%, because I definitely didn't feel like we answered 41%. I mean, oh, you know what I should do? So if I remember the score correctly last time, it was 17 out of 21. So basically, we just make it 17 out of 25, which would mean it's much more fair. 68%. And we didn't even answer the 7 marker, so I'm not going to try and like say that should be included there. So 68%, I'm not annoyed about that because I'm not going to make it like yellow because basically this score thing is just a measure of like the color of the score is just a measure of whether it was done thoroughly, and then the percentage is an indicator of obviously how well I did there. And then transition metals we will do a bit later. It's getting quite late, but I would hope we have time. But yeah, essentially that time was just spent reading the notes and getting 2 questions wrong. But in fact, there's nothing wrong with that because it's just improvement. So I'm pretty happy with that, actually, even though we did not get either of the questions and we spent a long time really doing nothing. Okay, that'll be all for this one. And I'll be probably back for another video quite soon for transition metals, and maybe trying to get the 6 marker NMR question that we didn't do done, and maybe those bottom ones, just so we can be thorough with our topic. We did read through the whole thing, so it should be alright. Okay, that's all.